It does.
Super admin.
It does, that sort of thing, yeah. Okay, so you're on. So,
but does that mean I'm both on, eyes on, and on YouTube tonight?
you could be, people could join that room, but I haven't told anyone that it's going on now. So, and I also haven't shared the YouTube link. So I'm just going to double check that that microphone volume is okay, because you've got quite a soft voice, haven't you?
Yep.
So if you want to crack on and just talk, I will go and watch live stream and see what the volume is like.
Okay. Are we live, Tom? All right, so this is CIE Chemistry, the AS paper, paper 1, that's the multiple choice, from 2013. All right, so question 1, easy one to start with. It's just asking for the oxidation state for chlorine. The thing you need to know here, of course, is that your rules for oxidation states is that oxidation number for oxygen, the oxidation number for oxygen is usually -2. And so you can just look across here. Well, if oxygen is -2, to get an overall charge of 1- there, then you need to have oxidation state for chlorine as +1. So it could be that one there or that one there. For this ion here, the overall oxidation state is -1. So the chlorine oxidation state there has got to be +5. So we must be either that one or that one. And we can see quite clearly that we're getting down to answer C already. Just confirm that. Oxidation state for chloride ion, of course, is -1. So that gives us answer C. Question 2. The key here is that you need to know that equal volumes of gas contain equal numbers of particles. And they're asking you to apply that to methane and to ethane. So you just need to have methane. You know that when that reacts with oxygen, it's going to make carbon dioxide and water. That's a simple combustion reaction. And you've got a stoichiometry of 1 lot of methane to 1 lot of carbon dioxide. So if you've got a stoichiometry of 1 to 1, then if you've got 10 centimeters cubed of that, you're going to get 10 centimeters cubed of that. Same applies for ethane, C2H6. This time we're going to be making, for each mole of ethane, we're going to be making 2 moles of carbon dioxide. I haven't balanced these equations, but you can see the stoichiometry for carbon is correct. And on this occasion, if we have 10 centimeters cubed of that, stoichiometry is 1 to 2, we'll end up with 20 centimeters cubed of carbon dioxide. Add those together, 20 plus 10, that gives us 30. We're going to get 30 centimeters cubed of gas. So that's the answer there. All right, next one. This is the industrial production of aluminium. And they've got 4 answers here. There's some distractors in there. First one, aluminium ions are oxidized in the process. Well, that's not right, is it? Because you've got aluminium 3+, that's gaining electrons to make aluminium. And you need to have in your mind the mnemonic oil rig. It's gaining electrons, oxidation is loss, reduction is gain. So this is aluminium 3+ being reduced, it's gaining electrons. So aluminium is not oxidized in the process, it's reduced. Then you've got to work out whether this process is happening at the anode or the cathode. For me, the way to remember this is cations in electrolysis go to the cathode and anions go to the anode. So you see those words match up. 3+, aluminium 3+, that's a cation. It must be going to the cathode. So anode is definitely wrong for that one there. Cryolite, you need to remember that that's not aluminium oxide at all. It's the, if you like, the solvent that's being used to dissolve up the aluminium oxide. So we've got that one was wrong, that one was wrong, that one was wrong. Process of elimination, this one must be right. Process that's happening there is the anion, O2 minus, is going to the anode, which is made of carbon. And when it gets there, we're going to make carbon dioxide. So the graphite anode does burn away. So the answer there is D. Okay, so you've got to use a data booklet for this one. We can just talk through it here, talking about first ionization energies. And you could look some of these up in the data booklet, but really you should know that if this is the periodic table, try and draw that, that's generally the shape of the periodic table, that ionization energies are increasing across a period, and they're increasing up a group. All right, so this is the first ionization energies. And they've given us 4 elements. We're not that familiar with them. We have to sort of plot them on our periodic table. We can look that up in the data book. And if you do that, you have these 2 periods here. And right over here in the inert gases, you've got radon. It's there. And then in group 1 and group 2, you've got francium, and you've got radium there. Okay, so you can see if we look at the periodic table here, we've got ionization energy, the first ionization energy, which is being increasing across a period, up a group. Well, the one out of these that must have the highest ionization energy is obviously radon, this one over here. Then when you compare these two, as you go across a period, then this one has got the next highest ionization energy. And then the smallest ionization energy is francium, like that. So I've written them here in order of decreasing ionization energy. They're asking here in the table for increasing, so we just have to reverse that order. And that gives us francium, radium, and radon. So the answer there is 4A. Okay, next question. Another easy one at the beginning. You've just got to work out the number of protons, neutrons, and electrons in all these different species here. For me, you just need to have a column of protons, a column for neutrons, and a column for electrons, and you fill that in. For example, aluminium. The 27 is the mass number, 13 is the atomic number. So you've got 13 protons, subtract those 2 numbers, you've got 14 neutrons, and the number of electrons must balance the number of protons in a neutral atom. We've got 13 there. And the question is asking us which species are all these numbers different. So it's definitely not that one there. And you can work through all of these, and eventually you get to this potassium ion. Okay, and you've got the atomic number is the number of protons, so there's 19 of those. The difference between the mass number and the atomic number is the number of neutrons, you have 20 of those. And to get a +1 charge, well, in the neutral atom, it would be 19 electrons, but we've removed one of those to give us the potassium cation with a single positive charge. So we have 19 protons, 20 neutrons, and 18 electrons. Are they all different? Yep, they are. So without working through the others, you can do those yourself. You can see that this one has different numbers of protons, neutrons, and electrons. Question 6, nice easy one again, really applying GCSE knowledge. It's looking at this reaction here, and it tells you that it's quite slow, but if you add acid, then the reaction goes faster. So you've got to think, well, can I see acid anywhere in that equation? There's no hydrochloric acid there. So it's not one of the reactants. And if it's not a reactant, but it's increasing the speed of the reaction, the rate of the reaction, well, that's GCSE knowledge, that must be a catalyst. So we're increasing the rate of the reaction by adding a catalyst, hydrochloric acid. Okay, next one, question 7, talking about activation energy and enthalpy changes here. And for this one, first up talks about the reverse reaction. So we need to look at the reaction profile going this way, because the reaction profile is usually written with the forward reaction going from left to right. But for the reverse reaction, we've got to go from right to left. And the activation energy for this reaction, going from right to left, is that distance there. The activation energy for the forward reaction is that distance there. And so actually A is correct, because the activation energy to get from here to the top of the transition state, you can see that's 50 plus 30 kilojoules per mole. We're going for the reverse reaction. The activation energy, it's that distance there. Okay, question 8. Again, we can try and extend GCSE knowledge here. Why does the rate of a gas reaction increase when the pressure is increased? Well, if you increase the pressure, you're squashing the gas particles into a smaller space, and that's like increasing their concentration. And you know from your work at GCSE that if you increase the concentration, you have more collisions, and that leads to a greater rate of reaction. And so D is our answer here. We've got the same number of particles, but in a smaller space. We've increased the pressure, and that means we have more frequent collisions between the particles, and that's the reason that the rate of reaction increases. All right, keeping on going, question 9. Talking about the difference between an ideal gas and a non-ideal gas. So we've got 4 gases here. Which one's going to be least like an ideal gas? Well, the principle of an ideal gas is that there's lots of particles in the gas, but there's no forces between the particles. That's the kind of assumption, really, for an ideal gas. But if you look at these in reality, you could say, well, we've got helium, it's a monoatomic gas, hydrogen, diatomic, you've got nitrogen, diatomic, and you've got carbon dioxide. And for all of these 3, those molecules or atoms are non-polar. There's nothing about these that gives them an end of the molecule that is slightly positive or slightly negative, except when you get to carbon dioxide. That's got 2 oxygen atoms either side of the carbon. The oxygen atoms are slightly negative, and the carbon atom is slightly positive. And that polarity is present in carbon dioxide, but not present in any of these other molecules. And that means we can get permanent dipole to dipole interactions between the carbon dioxide molecules. And those permanent dipole-dipole interactions are stronger in intermolecular forces than the transient dipoles or London forces that you have between these non-polar molecules. So for carbon dioxide, that's going to behave not like an ideal gas, because there'll be some forces between the molecules of carbon dioxide because of these permanent dipole interactions. So which is like a least ideal gas? It's carbon dioxide. Okay, last one on this page here. You've got to know that the form that you're familiar with of the ideal gas equation is this. You've got the pressure, the volume, the amount, that's N there, that's the universal gas constant, and T, that's the temperature in Kelvin. And you just got to do a substitution, because you also know that the amount of substance is equal to its mass divided by its molar mass. That's the molar mass at the bottom, a large M. And if I substitute the mass divided by the molar mass for the amount, the N in there, then I end up with pressure times the volume is equal. Now we've got the mass divided by the molar mass times the universal gas constant times the temperature. And if I arrange all of that to make M, the molar mass, the subject of the equation, molar mass is there, and I've got the mass, the universal gas constant, the temperature in Kelvin, and I've divided both sides by the pressure and the volume. And so the closest one we can see up here to what I've got there is actually here, C. And strangely enough, in the exam paper, they've put MR, which isn't strictly the molar mass. It's not really the molar mass. That's not correct. MR is the relative molecular mass. And actually, these two values, as you know, are numerically the same. The relative molar mass is unitless, but the molar mass has units of grams per mole. And strictly speaking, the answer to this question is the molar mass in grams per mole, not the relative molecular mass, which is a unitless number. But I think we know what they're getting at there. We're expecting this value of the relative molecular mass should be the molar mass is now the subject of that equation. We've rearranged it, and we've got that one there. Good. Question 11. Okay, you've got a reaction here of iron 2+ ions and these manganate ions over here. So just let me give myself a bit of space down here. What you've got to do is, the question is talking about oxidation, isn't it? You've got the SN2+ ions being oxidized to SN4+ ions. And whenever you have an oxidation that's accompanied by a reduction, this is talking about a redox reaction. And you can think about redox reactions as a reaction of two halves, the oxidation half and the reduction half. So let's look at those then. So you've got this one, they tell you about that in the question. You've got tin 2+, haven't you, going to tin 4+. And so the oxidation number there for tin is going from +2 to +4. Well, the oxidation number is going up. And if it's going up, that means there's an oxidation happening. And you need to know the mnemonic oil rig, meaning oxidation is loss of electrons, reduction is gain of electrons. Now this is oxidation, it's a loss of electrons, so the electrons are going to go on this side of the equation, and they go there, all right? And because we're going from 2+ to 4+, and able to balance the equation, we have two negative charges there. And you look at each side of the equation, and you can see both sides have the same charge. 2+ there, 4+, 2-, overall 2+. So we know that's right. From the manganate ions, let me just have some space up here. You've got those ions there, and it tells you in the question that they're going to Mn2+. Work out the oxidation number of manganese. Here, it's going to be +7. Over here, it's +2. So the oxidation number is going down. If the oxidation number is going down, that's a reduction. Excuse my writing. Reduction. And we know from our mnemonic that reduction is gain. It's a gain of electrons. So electrons are gained. And if electrons are gained, they've got to go on this side of the equation. Now, we've got to balance this up. The only way we can do that in a acidic solution is to add water to balance those 4 oxygens on the left-hand side. There goes the water. I need 4 oxygens, so I'm going to have 4 waters, and that must mean I've got 8 acid on this side. And to balance the charges, you can see I've got 2+ over here. I need to get 2+ over on the left-hand side. If I have 5 electrons, add up all those charges, that comes from overall charge sum of 2+. So you can see if I compare the oxidation that's happening here and the reduction that's happening here, the two halves of the redox equation, then to combine those two, I've got to multiply that one by 5 to give me 10 electrons, and then multiply this one by 2. That gives me 10 electrons altogether as well. And then when I add those two together, the electrons will cancel out. There's 10 here and there's 10 there. And I could add those two half equations together to give me a full redox equation. And so the stoichiometry, you can see, is I'm going to have 5 lots of tin and 2 lots of manganate. So I've figured out by combining the two half equations what the stoichiometry is. Now, it tells us up here how much tin that I've got. It tells us the relative molecular mass. I can easily change that to the molar mass, and I can work out that if I do that, then the number of moles of tin is 0.05 moles of tin. And because we've figured out the stoichiometry of 5 tin to 2 manganese, well, if I've got 0.05 of a mole of tin, then I must have 0.02 of a mole of the manganate. So we figured that out by doing the two half equations, the reduction and the oxidation, and seeing that if I want to remove the electrons or balance the electrons, I have to multiply this one by 5 and that one by 2, add them together, and gives us a stoichiometry of 5 tin to 2 manganate. All right, next one, question 12. Again, we're using the data booklet, and it's telling us, it's pointing to bond enthalpy data. And so these kinds of questions, you know that you've got to calculate by seeing bonds that are broken and bonds that are formed. So in the reactants, bonds are broken, aren't they? And here in the products, bonds are formed. Sorry, my pen's just lost it there. Bonds formed. Okay. And when you're breaking bonds, you're taking energy in, so that's endothermic. And when you're forming bonds, well, that's the opposite of breaking them, so that must be exothermic. So what you do is you write down here all the bonds that are broken, and you write down here all the bonds that are formed. And because these are endothermic, we're taking energy in to break bonds, the sum of all the bond breaking is going to be positive. And here we're forming bonds, so the sum of all the bond forming is going to be negative. And you look all those up in the data book, and you end up with the total energy that you put in to break the bonds is 2,632, kilojoules per mole. That's how much energy you need to put in to break the 4 hydrogens and the 2 bonds between the oxygen atoms there. And the bonds that are formed, if you calculate all that together, then you get 3,320 kilojoules per mole. And so the difference between the energy that you had to put in to break the bonds and the energy that you got out when the bonds formed is on the product side. You've got more energy out than you put in. So as we'd expect, all these values are negative. And if you find the difference between those two values, the answer is D. So all you're doing is looking at the energy difference between the energy you have to put in to break bonds and the energy that's given out when bonds form. Okay, 13 is a little bit nasty because at AS level, you're just expected to know this fact about the solubility of compounds in the group 2 group. When you get to A2, you work through the reasons behind all of this, but AS level, you just need to know that as you go down group 2, then the solubility of hydroxides, I'll just do that, increases. But as you go down group 2, the solubility of the sulfates decreases. So you now need to look across here, and it's going to be the answer there, because comparing magnesium and barium, barium is further down group 2 than magnesium, and we're looking at hydroxides here. So the solubility is increasing as we go down, so that's correct. And for sulfates, as you go down, they become less soluble, So magnesium sulfate will be more soluble than barium sulfate. So row C here is the right answer. And this solubility of the sulfates becoming less soluble and the hydroxides becoming more soluble as you go down the group is just a kind of fact that you need to know at AS level. And we'll get into the details of why that is in A2. Okay, next one. These are so-called displacement reactions. And again, you can just use your GCSE knowledge here to help you a bit. When you studied the halogens at GCSE, you knew that the most reactive element was at the top of the group. So fluorine is more reactive than chlorine, chlorine is more reactive than bromine, bromine is more reactive than iodine. And you also knew that typically these halogens, what am I doing? That's form a singly negatively charged ions. So you need to recall your mnemonic for oxidation and reduction, oil rig. So these are gaining electrons, aren't they? So when fluorine gains an electron, that's fluorine's being reduced. So, and we're comparing, aren't we, in this example, bromine and iodine. And it says we've got iodine in solution and we've got bromide ions. Now, what it wants us to think about is, well, is this reaction possible? Can iodine go to iodide ions? And can bromide ions go to bromine? You can see that this one is gaining electrons, must be 2 electrons there to balance, and this one must be losing electrons. So oxidation is loss. So that's oxidation, and that's reduction. So you can see here that as you go up the group, the halogens are more likely to gain electrons. And so it's very unlikely that iodine is going to gain electrons at the expense of bromide. So we'd say, based on our kind of discussion there of reactivities of halogens and which ones are most likely to lose and gain electrons, that this is very unlikely because iodine is not likely to lose electrons compared to bromine. Okay, this is a pretty easy question here. Question 15 is talking about an element that you probably haven't come across. It's in group 7, so one of the halogens. And it's just talking about the oxidation. So if other halogens that you know about would be, say, chlorine. And if we were in sodium chloride and you'd have a chloride ion, if that was being oxidized, it would be going to, that wouldn't it? The oxidation is going up, it's being oxidized. And astatine is going to behave just like chlorine. So it's going to, when it goes from an anion to the element here, then it's losing an electron, it's being, the oxidation number is going up, it's being oxidized. And so the answer there is astatine. Okay, question 16. What you need to know here is the thermal decomposition of magnesium nitrate. So this is just something that you might be able to work this out from the question, because it says magnesium nitrate will decompose, gives a white solid. We might guess that's magnesium oxide, and it's going to give her a mixture of gases. And one of the gases is some oxide of nitrogen. We can probably guess, if we didn't know, nitrogen dioxide. It's a mixture of gases. There's something else there. If you balance this up, you get that as your stoichiometric coefficients. So that's something I think that you've really got to know from your studies on group 2. If you didn't know it, you could probably figure it out a little bit, because you know that magnesium oxide is a white solid. We need a mixture of gases. We've got nitrogen dioxide and oxygen, and one of the gases, it says an oxide nitrogen. So that, if you didn't know it, that would be a pretty good guess. So you've got a stoichiometry here, and you've just got to go from, you know what the mass is. You can look up in your data booklet the relative molecular mass, and from that convert the molar mass, and you can then work out the amount, the number of moles, because you know the number of moles is the mass divided by the molar mass. And if you do that, we had a mass of magnesium nitrate, and they told us to begin with that that's 7.4 grams. And if you work all that out, you realize that you've got 0.05 moles. The amount is 0.05. And then you've got this stoichiometric ratio that there's going to be twice as much nitrogen dioxide in terms of amount as you had the amount of magnesium nitrate. So twice that is 0.10 moles. And then you can look up the molar mass in the data book of nitrogen dioxide. That's actually 46 grams per mole. 0.1 times that gives you 4.6 grams of nitrogen dioxide, which is that one there. Okay, question 17. Just scroll up a bit. Okay, so in this one, they're testing your knowledge of the kind of tests that you do in inorganic chemistry. And what they're really testing here, and just write, is if you've got, say, sodium chloride, sodium bromide, sodium iodide, if you're testing for these ions, the way you distinguish between them is, first of all, you add silver nitrate solution. And you can see that's what they've done in the first step. And the thing is that you get a precipitate with all of these, and this precipitate with chloride is a white color. The precipitate with bromide is cream, and the precipitate with iodide is yellow. Now, they're all, I mean, you can see the difference between them, but it's not that distinct. It's not like the difference between red and green or something like that. You've got white for the chloride, cream for the bromide, yellow for the iodide. So you can sort of tell the difference in the colors of these precipitates. But there's a further test that you should know, that you can then add ammonia solution. Now, if it's dilute ammonia, this dissolves. If it's concentrated ammonia, excuse the pen here, if it's concentrated ammonia, then that precipitate dissolves. And down here, it doesn't matter whether it's dilute or concentrated, nothing's going to happen at all. You don't get anything dissolving. So if you couldn't really work out the colors here, they're quite close to each other. If you had dilute ammonia, then it must have been a chloride precipitated. If you needed concentrated ammonia, then it must have been a bromide that formed the precipitate. And if it doesn't, precipitate doesn't dissolve at all, then that must mean that it was an iodide that formed the precipitate. Now, when you look up here, well, they all form precipitate. Well, that gets us that first stage there, and it didn't tell us about the color. But then it says those precipitates then dissolve in dilute sodium, dilute ammonia. Now, the only one that dissolves in dilute ammonia is this one, the white precipitate that was formed from a chloride. And as you look down the group, the selection here, there's only one chloride given to you, so the answer there is A. Okay, good. So this is just another thing that you really need to know. It comes up quite often in exams, and they're trying to test you on what are the things that change the value of the equilibrium constant. Okay. Now, increasing the pressure, well, that's a bit like increasing the concentration. That doesn't change the value of the equilibrium constant. Removing product from the equilibrium mixture, well, that's like reducing the concentration, and that doesn't change the equilibrium constant either. A catalyst, you need to know, does not change the equilibrium constant. It just changes how quickly equilibrium is established. And so the only one that's left that really does change the value of the equilibrium constant is the temperature. And when you see equilibrium constants, they're always quoted at a particular temperature, because the temperature is the one thing that will change the value of the equilibrium constant. All right, 19. Again, this is a bit like it's kind of the lab, the sort of bench tests that you might do when you're trying to figure out an unknown compound. And your test for ammonium, this is, I lost my pen again. So this is ammonium sulfate, NH4, SO4. And so you've got this ammonium ion here, NH4+. And you should know a simple test for the ammonium ion. And the simple test for that is to add normally sodium hydroxide. And the principle here is that a strong base will displace a weak base. So add sodium hydroxide, and instead of having the ammonium ion, you get displaced ammonia gas. So that, and you can test for that. So this is the background to this question, is the test for the ammonium ion. Add normally sodium hydroxide, and you get ammonia gas given off, which is quite distinctive. Now, you don't have sodium hydroxide down here at all. So this is where you need to do a little bit of sort of chemical intuition, because we could see here, it wasn't particularly the fact that it was sodium hydroxide, the strong base, that was liberating the ammonia, but all we need is something which is going to give us this strong base, even if it isn't sodium hydroxide. Now, it's obviously not dilute hydrochloric acid. Lime water, you might know from GCSE, is actually a solution of calcium hydroxide. So that's pretty similar. It's got the OH minus, it's got the hydroxide. So that's the one that's going to liberate the ammonia. It's a strong base displacing the weak base. And these other two are just distractors. They've got nothing to do at all with testing for the ammonium ion. Okay, next one, question 20. So I'm giving you a chemical that you've not come across before, but you need to know about cis-trans isomerism and optical isomerism. Now, the cis-trans isomerism is all related to the inability of compounds like this to rotate around a double bond. You can't spin these ends. You can't rotate around the double bond. And cis is looking for something that's on the same side, and trans is looking for something which is on opposite sides. So we're looking for something here which gives us something which is on the sort of opposite sides of this double bond. And the optical isomerism is when you've got a single carbon atom, and it normally has four different things, four different atoms or groups bonded to it, and they've all got to be different. And that's known as a chiral carbon. And if you look across here, well, that's not, is it? That's not a chiral carbon, because you've actually got two bromine atoms there. We're looking for four different things. And over here, well, you've got four different things. That's possibly a candidate. Over here, you've got four different things added. And over here, you've got four different atoms on the chiral carbon here. So then you've got to start looking at the cis-trans isomerism. So we know that one's out. And here you've got identical species bromine atoms on that carbon there. So the only thing that really has trans isomerism, where you've got a difference going that way, because that's trans, is this one here, B. Because, okay, you've got that there, but you've also got that there. And you've got the same thing happening here, that you don't have cis-trans isomerism, except you've got it over here. And so our compound B is going to be the one which has the cis-trans isomerism and the optical isomerism, because we have 4 different atoms or groups bonded to that carbon atom there. Okay, again, looking at probably a chemical that you haven't come across before, you've got lactic acid, and you've got a reaction here with lactic acid. First one, you've got lactic acid reacting with an alcohol. Now, carboxylic acids do react with alcohols, and you should know that they make esters. So you need to look across here and see if an ester has been made. And actually, that's not an ester in there, but that's a very similar spelling. That's an ether has been made. So that's not true. We're looking for a reaction here, and that would be making a carboxylic acid and an alcohol. It's making an ester. It's not making ether. So that one's not right. Now, this next one, we've got 2 carboxylic acids. And so there's a possibility, again, of making an ester between the methanoic acid and the alcohol that's there. And so you're going to get, this is the ester group here, you see. And so it's a bit awkward to see, but you've reacted the methanoic acid with the alcohol on the lactic acid, and you have genuinely made an ester there, because the ester's gone on there. Okay, so that's, I mean, that we know that one's wrong because we ended up with an ether. That one's looking good. This one down here, they're kind of giving you a distractor here, because sodium hydrogen carbonate does give you water and carbon dioxide with a carboxylic acid, but it doesn't form this kind of sodium salt of an ether. It's the same kind of problem that you had up here. So we were expecting there to have the reaction between a carbonate and an acid. So we've made some kind of sodium salt of an ether again here. So that one's wrong also. And this last one is a distractor, because that reaction is a reaction that's not going to happen at all. So you've got the answer there is B, because you've generally got an ester reaction between methanoic acid and the alcohol group on the lactic acid. So the answer there is B. Just try and scroll up. Okay, so now they're testing you here on your mechanisms. And you've got, this is the one that you see in all the textbooks, you've got ethene, that's one of the starting reactants. And you're looking at the reaction with bromine. And what you need to know is that when the bromine molecule approaches the ethene, then this high area of electron density here is sufficient to momentarily polarize the bromine molecule. That's so negative in the middle there, so much electron density, that it forces this molecule to be slightly negative down there and slightly positive down there. And that means that you can then get this kind of reaction happening, where a lone pair of electrons is going to move from that double bond there, and then you're going to get a lone pair of electrons moving that way as well. So the intermediate, you see, is going to be this, where this was the ethene. Now you've got a new bond that's formed to bromine, and you've got the hydrogen atoms, nothing's happened to those. And because a bond pair of electrons has moved to form the bond there, then that has now got a positive charge. And because the pair of electrons moved in, both of them moved from the bond that was formed between the two bromine atoms there to this, you've now got a bromine ion, and it's got all those lone pairs around it. That's the intermediate. And later on, that bromine ion is going to get attracted to that positive center there, and we're going to end up with the final product, which is going, so I can show we've got a lone pair of electrons going in there. We've got the final product, that's the carbon, isn't it? You've got the hydrogen there, and you've got the bromine added on there, the bromine adding on there. We've got 1,2-dibromoethane, and the intermediate had a positive charge on it. So what's the correct description of the intermediate? Well, it's got a positive charge. And anything that's got a positive charge is going to be attracted to negative charges. And so if it's seeking negative charges, if it's looking for negative charges, a bit anthropomorphic, but it's electron loving, or it likes electrons. It's positive charge, it's going to be attracted to the negative charge there. And so this word here, electro, that's the negative electrons, and phile, like bibliophile is somebody who likes books. Electrophile is a species that is going to get attracted to, it likes electrons. So this intermediate, because it has this positive charge, it's going to be attracted to electrons. It's an electrophile. Okay, chloroethane is used to make a solution of sodium propanoate. And what you've got to watch here is you're starting off with ethane and you're ending up with propanoate. And you know from your naming of organic compounds that the eth bit there refers to 2 carbons in a chain, and the prop bit there refers to 3 carbons in a chain. So there's a clue here that there's something about this whole question which is extending the length of a carbon chain. So you need to look down here then, and these things are obviously wrong. There's nothing in them that can help us extend the carbon chain from 2 carbons to 3 carbons. So you've got a choice here, and hydrogen cyanide is HCN, and potassium cyanide is KCN. And you can see these reagents do have an additional carbon, and that's going to allow us to extend the chain length from 2 to 3. Now, so just look back through the question. Hydrogen cyanide is a gas. Potassium cyanide, you can make a solution of that. You're boiling here. You're in aqueous solution. You're talking about hydrolyzation there. So the only one that's really a candidate is potassium cyanide, because that's something that you can dissolve in water. So you've got potassium cyanide there. It's got the additional carbon atom. It can add to the chain. And just to write out the reaction, if this is our starting reagent, we've got chloroethane, haven't we? So there's a chlorine on there. And it's just going to be a substitution reaction where we've got Cn minus, because you've got potassium plus Cn minus. You've just got a substitution reaction, and you're going to get this, which is called a nitrile. And you can see there, I've extended the carbon chain. We started off with 2 carbons, now we've got 3. And if we boil that with sodium hydroxide, then that then becomes carboxylic acid. And we've used the potassium cyanide to extend the chain. And that's like a common part of organic synthesis. Whenever you want to extend a carbon chain, you're typically using the potassium cyanide. And then you can, for example, you can make the carboxylic acid. Okay, so more organic mechanisms now. We've got 1-bromopropane, and we're wanting to make propan 1-ol. You can see we've got prop again, Where's my pen gone? So we've got, I've lost my pen. Come on. And there we go. Okay. So we're not extending the carbon chain this time, are we at all? We're just going from a 3-carbon chain to a 3-carbon chain. And you've got to know that you start with this 3-carbon chain. I won't draw in all the hydrogens for the moment. And it starts off with the bromine there. And you've got the hydroxide. And you can see that because bromine is more electronegative than carbon, you can have slight negative there, slight positive there. And that means that this, which is a nucleophile, is going to have a lone pair of electrons that can start to form a bond there. And because this bond is forming and that one is breaking, you've got an intermediate where you've got a new bond forming from the hydroxide ion that's attacking, and a bond that's breaking from the bromide ion that's leaving. So if we look down this list of questions here, so how should the first step in the mechanism be described? Well, we're going to draw a curly arrow from the lone pair of electrons on the hydroxide ion to the slightly positive charge. So that's really good, isn't it? That looks like a good one. Now, we're not going to be drawing a curly arrow from the carbon atom. There's no lone pair of electrons for us to use there, so that's obviously wrong. And we can see that the reaction is happening because the lone pair of electrons is starting there, and so there's no curly arrow being drawn this way. So that one's wrong. And this is wrong as well. Homolytic fission means that the pair of electrons in a bond, one electron goes one way, one goes the other. But here we've got a pair of electrons that are moving. So we're not having homolytic fission, we're always getting heterolytic fission. So that's a distractor as well, that's obviously wrong. And so we've got, these are all wrong, that one's right, A is our answer there. All right, so we've got pentane reacting in ultraviolet light with chlorine, and we're going to get various different compounds formed. And we've got one chiral carbon atom. Now we remember that the chiral carbon atom means that there's 4 different atoms or groups attached to a central carbon atom, and we're just looking for one of these. And if you look, we've got 5 carbons, haven't we? I won't draw the hydrogens in again, and it's saying we've got a chlorine there and a chlorine there. Now, if you draw the hydrogens on here, that's clearly not chiral because you've got 2 of the same atoms there. But if you come over here, then you can see, well, this carbon atom has got a chlorine atom there, a hydrogen atom there. It's got all of this on the left-hand side, and it's got something different on the right-hand side. So that means that you've got a chiral center there. So it's true that when you have the chlorine added to the position number 1 and position number 3, then you're not getting a chiral carbon there, but you are getting a chiral carbon there, and we just need one chiral carbon atom. Now you can go through the other ones and satisfy yourself that they actually don't give you a single chiral carbon, and it's this answer here that gives us the right answer to question 25. Good. Okay, so on this one here, you're talking about ethanol, and you're using potassium dichromate. You need to know that that's an oxidizing agent. You can see what I mean there, oxidizing agent. And so when you have an alcohol, such as ethanol, and you're oxidizing it, you end up with the carboxylic acid. Okay, so you oxidize an alcohol, you get a carboxylic acid, and you're given the mass there, can't you? You can use the data book to work out the molar mass. You can work out the amount, the number of moles, and you're going to have a one-to-one stoichiometry here. So the number of moles of carboxylic acid will be the same as the number of moles as you started with the alcohol. And then you can work out, then you've got the number of moles, you can work out the molar mass, and then you can work out the mass of the ethanoic acid that was formed. So that would assume that you didn't get any waste products, the reaction went to 100% completion, you didn't lose anything. But actually, life is a bit more messy than that. The yield of the product ended up being only 60%. So whatever your mass was there that you worked out, you've got to have just 60% of that mass. And when you work through all of that, then you find out that actually 60% of the mass that you had turns out to be 1.80 grams. Okay, another compound down here, you can see that that functional group is a ketone. That's that one there. And this one is an aldehyde. Okay, ketone and aldehyde. And you've got to find a reagent that's going to react with one of these functional groups. So it's going to react with the ketone, but not the aldehyde, or it's going to react with the aldehyde, but not the ketone. And the trick here is to know that the aldehyde can be oxidized. If you oxidize an aldehyde, then you get carboxylic acid. But you can't oxidize a ketone. There's nothing you can do there. So the oxidation will distinguish between the ketone and the aldehyde. And so 27A is the right answer there. Acidified potassium dichromate is oxidizing agent. It'll oxidize the aldehyde. It won't oxidize the ketone. Okay, so this one is a bit odd because what they've done is they've drawn a structural formula here, and it looks really, really odd because there's some kind of oxygen atom between the carbon there and this carbon chain here. And because that looks odd, you've got to have your radar immediately sort of spooked by that. And what's happening there is they've drawn an ester, but they've drawn it kind of back to front, because normally with an ester, you would draw the carboxylic acid group there, and then you would do, what's this, C3H7, isn't it? Okay, so, and you've got the methanoate group there, and 3 carbons is propan, isn't it? And so this is an ester, and these esters are named kind of back to front when you write the formula out like that. Normally you have the part that came from the carboxylic acid on the left and the part that came from the alcohol on the right, and they're just drawn it back to front here. And so you call that propyl methanoate. So you use the propyl part first and the methanoate part second. So you've got propyl methanoate. So it's going to be one of these two here, isn't it? And the other thing they want you to do is compare the boiling point of this propyl methanoate with butanoic acid. Now, butanoic acid is 4 carbons. It's but, isn't it? And you've got that carboxylic acid on the end. And what you're looking out for here is that because you've got a hydrogen linked to an oxygen, then you can get hydrogen bonding. But over here, you can't get any hydrogen bonding. There is no hydrogen linked to an oxygen. If you look around there, there's lots of hydrogens and oxygens, but they're not linked to each other. And so butanoic acid will have hydrogen bonding, but this propyl methanoate will not. And it's this hydrogen bonding that forms strong intermolecular forces. And when you get strong intermolecular forces, then it's much harder to break those forces. You need a higher boiling point. You need more energy to break the hydrogen bonds. So butanoic acid will have a higher boiling point compared to the propyl methanoate. So you end up with this one here, where propyl methanoate has a lower boiling point because of the hydrogen bonds that exist in the butanoic acid. Okay, very easy. The next one. For these ones, all you have to do is know that I've lost it. There we go. Okay. You have to know that when you have a double bond, it doesn't really matter what these things are on here, that's a double bond. When that polymerizes, you just get the double bond forming a chain. And whatever was hanging off the chain just hangs off, sorry, what was ever hanging off the double bonded carbon there just ends up hanging off the chain that forms. So if you look through all of these, you're starting with this, and hanging off the side there is this group. And the rest of it is just hydrogen atoms, isn't it? And so when that polymerizes, you're going to get the chain of carbon atoms, and you're going to get that hanging off the chain. So the repeat unit ends up being that to there. That's the repeat unit. You could say there's n of those. So if you look through all of these, well, the repeat unit is going to be B over here. All right. I'll just rush through these ones at the end of running out of time now. Okay, so we're looking for this trans behavior here, where we're getting something different across the double bond. So the trans is going to be either that or that. These aren't trans at all, those are cis. Okay, and then we're looking for something that's optically active. It's very similar to the question we had earlier on. So we're looking for the carbon here to have two different groups. Now, you see this carbon atom here has got hydrogen, and it's got all of this hanging off on the left, but above and below, those are identical. So that doesn't have four different groups or atoms bound to it. Come over here, you can see actually that, because it says R1 and R2, they're different. So the carbon atom here has a hydrogen atom there, a different group here, a different group here, a different group here, four different atoms or groups attached to the central carbon atom. So that one is both trans and that's optically active. It's got a chiral carbon. So 30, answer is B. Now, when you get down to section B, you've got these rather more complicated questions to do, where there may be more than one answer that's correct. So we're looking at free radicals. We know they have unpaired electrons. It says some free radicals have two unpaired electrons. They're called diradicals. Well, oxygen has 1, 2, 3, 4, 5, 6 electrons. Well, it's got two pairs of electrons in its outer shell and two unpaired electrons. So that definitely is a diradical. Chlorine, you can do the same thing. It's got 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. Got 3 pairs of electrons, 1 unpaired electron. It's not a diradical, it's just a radical, so that's not diradical there. And then CH3, well, you've just got all the carbon bonds to hydrogen, and then because you've got one of the outer shell electrons of the carbon which hasn't formed a bond, you've just got a single electron there. So that's a radical, but not a diradical. So we can cross that one out. Only one is correct. Answer to that is then going to be D. Okay, going on to group 2 metals. Group 2 metals have higher melting points than group 1 metals. Which factors could contribute to the high melting points? Well, the smaller interatomic distances. Well, that could. So that's definitely a possibility there. That means that the protons in the nucleus can be attractive to the sea of electrons that are delocalized more easily. The interatomic distances are smaller. It's true that there's more electrons from each group 2 metal atom than in group 1, because group 2 metal atoms, such as magnesium, you can get Mg2+, compared to sodium atoms in group 1, which is Na+. So there's 2 electrons from each atom that are delocalized in the metallic bonding. So there's more electrons. Yeah, that's the same as well. Now, this first ionization energy has nothing to do with the melting point of the group 2 metals, and so that is not really contributing to the melting point. So it's 1 and 2 there, gives us the answer. If you look on the table, gives us the answer B. Right, valence shell electron pair repulsion. Okay, you've got to use all of that information to answer this question. I'll just run through this here. Easiest way to do this is really to say, take boron, talking about its number of electrons in the valence shell. Now, if you look up the periodic table for boron, it has 3 electrons in its valence shell. Hydrogen has 1 electron in its valence shell, but there's 3 of those. So the number of valence electrons altogether is 6. So you can start to draw up, well, there's boron in the middle, hydrogen, hydrogen, and we've got 6 valence electrons. So there'll be 2 to form a bond there, 2 to form a bond there, 2 to form a bond there. So you've got boron surrounded by 3 hydrogens, and you've used up all the valence electrons. But if you look at phosphorus with 3 hydrogens, phosphorus has 5 valence electrons. It's got 3 hydrogen atoms as well. So the total number of electrons is 8. And so if you drew that one out, well, here's phosphorus, here's hydrogen, here's hydrogen, here's hydrogen. You've got, those are the bonds that are being formed. But oh, look, we had 8 valence electrons. So we've got to have a lone pair of electrons in there. And so with this one, you've got 3 electron domains. And so that's the electron domain geometry. The molecular geometry is those are all repelling each other equally. You've got boron in the middle, and you've got one coming out and one going behind. You've got all these hydrogens in a plane around a central boron atom. There's no lone pairs of electrons. So the molecular geometry is the same as the electron domain geometry, and that's trigonal, the 3, planar. They're all in a plane. But when you come down to phosphorus, the electron domain geometry is tetrahedral. You've got a lone pair of electrons and 3 bond pairs of electrons. So actually, this substance ends up like 3 legs of a tripod. And you've got a lone pair of electrons up there, and there's a repulsion between all these bonds. So these bonds are getting forced downwards by the repulsion that they have with a lone pair of electrons up there. So if we look not at the electron domain geometry, but there's my rubber, the molecular geometry, you can see that we've got still 3, so it's trigonal, but these are like the legs of a stool, a pyramid. So that's actually trigonal planar. And so if you work in a similar way through with all of these, you find that one, as we did, was trigonal planar, that one was trigonal planar, but that one ended up being trigonal pyramidal. Did I write that wrong? Sorry, pyramidal. That's trigonal pyramidal. So we end up there with answer B because only these 2 have a planar structure. In the molecular geometry, that's actually a little pyramid, a 3-legged pyramid. Okay, the easiest way that I find to deal with these is it's telling us that these are the first ionization energies of the 20 successive elements in the periodic table. So you could just look those up in the data booklet if you wanted to, but you start off with hydrogen, 1s1, helium, 1s2, and then after 1s2, you've got 2s1, 2s2 we've got there into group 2. Now we're getting 2, that's 1s2, 2s2, you've got 1s2, 2s2, 2p1. That's going to be, continuing on here, will be 2p2, 2p3. I've missed out the 1s2 and the 1s2. Sorry, the 1s2 and the 2s2. You've got 2p4, you've got 2p5, you've got 2p6. And up there, you've got 1s2, 2s2, 2p6. You've got to the end of the period again. So you could just write the electron configurations in there to help you if you didn't recognize the shape. And B, yeah, they're in the inert gases, aren't they? They're in group 0. D, it contains 2 electrons in the outer shell. Yes, we've got 2s2, so that's correct. That's correct. And G, well, there's 6 atomic orbitals available. Sorry, there's 3 p atomic orbitals available, and they're half filled there because each atomic orbital can accommodate 2 electrons. So it's true that there's a half-filled p subshell at that point. So 1, 2, and 3 are all correct, and that gives you an answer of A if you look that up against the key. Okay, this one, if you work through it all, it's all your group 2 chemistry. That one is magnesium carbonate. This one is calcium carbonate. If you heat calcium carbonate, you get calcium oxide. And if you react calcium oxide with water, then you get calcium hydroxide. So that's all group 2 chemistry. Actually, it's pretty much GCSE group 2 chemistry. Now, because the molar mass of magnesium is less than the molar mass of calcium, if you had 1 gram of that and 1 gram of that, sorry, if you had 1 gram of that and 1 gram of that, then you'd actually end up, in terms of amount, the number of moles, you'd have more moles of magnesium carbonate. So it would neutralize more acid of the magnesium carbonate than the calcium carbonate. So that's correct. So W is magnesium reacts faster than calcium. Well, you need to know that as you go down group 2, the metals become more reactive. That's GCSE knowledge again. And if you add calcium hydroxide to the soil, you're adding hydroxide. That's a base. We'd expect the pH actually to increase because we're adding a base. So we don't expect the soil to decrease. We're making the soil more alkaline. So only one of those is correct. Answer D. This one, we've got hydrogen iodide, and that's going to hydrogen gas and iodine. And so we're breaking the bond between hydrogen and iodine. So what factors contribute? Well, the strength of the bond will. And actually, the strength of that bond is very affected by the size of iodine. Iodine is quite big, so it's quite a weak bond. If that was fluorine or chlorine, it would be a much stronger bond because fluorine and chlorine are smaller. So the size of the halogen atom is going to affect it. And these atoms are, sorry, these compounds are in their standard state. And so that the formation is going to be 0 for each of those. So actually, that one gives us 1 and 2 as the answers. Look that up in the key, gives you answer B. Okay, this one you need to know is the classic free radical reaction. You know that you start that and you end up with 2 chlorine atoms. You know that that's called initiation. And then you get propagation, where you have your methane and And then you can get your termination where you can have, say, sorry, I'm forming, so that's propagation there, isn't it? Like you started off with a radical and you ended up with a radical. And then you could have a termination reaction where those form ethane. So you've got your propagation steps, your initiation steps, your propagation steps, and your termination steps. And in all of those, well, hydrogen chloride could be made, dichloromethane could be made, but nowhere in initiation, propagation, or termination do you make hydrogen. So that's not produced at all in this reaction. And when you've got 2 and 3, the answer to that is C. Okay, last one here. You're talking about an oxidation reaction. Now, these are all aldehydes, aren't they? And only in those 2 is the aldehyde being oxidized. Here, it's just making a compound that's easy to identify, actually. So that one is oxidized, that one is oxidized, but here we're just doing a different kind of reaction, giving us something that's easy to identify. So when 1 and 2 are correct, the answer there is B. Almost finished, last page. Okay, here we go. All right. So, a lot of questions about esters actually in this paper here. Hydrolysis, lysis means breaking up, splitting up. Hydro means splitting up with water. We're going to split this ester up. And the ester gets split here. If this is the ester, it's going to get split at that point. And you can end up with a carboxylic acid and an alcohol. Okay, when you do the split. So you need to look through here and see if there's anything that's going to, if you split there, what do you end up with? Well, that would be the alcohol. That would definitely come out of the split, so that gets a tick. And this is the sodium salt of the carboxylic acid. So the carboxylic acid is coming out of the split as well. And because we've got sodium hydroxide around, we end up neutralizing the acid to give us the sodium salt. So that's there. But this one, you can see it's making the case that somehow we've removed a carbon atom from a chain. And we're not removing carbon atoms at all. We're just doing hydrolysis, splitting an ester up, lysis, using water. We're not removing carbon atoms from a chain. So that one is out of the picture. And when you have 38, in question 39, you have question 1 and question 2, then you've got answer B, a grain at that point. Last question then, you've got lactic acid, and you want to make the sodium salt of the lactic acid. Well, you can neutralize the acid with sodium hydroxide. You can do the same thing with sodium hydrogen carbonate. So that's going to definitely work. That's going to definitely work. But you could add sodium to an acid, but that's almost certainly going to cause an explosion. So I mean, you remember that from GCSE, adding sodium to water. It's a very violent reaction. We're not adding it to water here, we're adding it to an acid. And so you just add sodium to the acid, probably you get some kind of explosion, but you certainly don't need an excess of sodium. It's going to react straight away. So the key at this point, I think, is to the fact they're asking for an excess. And these two would react nicely with lactic acid in excess to give the sodium salt. You certainly don't need an excess of sodium to react with an acid. And so when you've got 2 and 3 together, that gives you answer 3. Sorry, answer 3? Answer C is the answer when you have 2 and 3 checked. All right, good. So that's paper 1 done. You get an hour for that, 40 questions. You're looking at about 90 seconds for each question. We've taken a bit longer from that during this run through, but we've had a chance to talk through everything as we've been through the paper today. Okay, thanks for listening, and look forward to speaking to you on the Slack channel.